Oh, this works. Okay. Hello. Is this working? I have no idea what's happening. Okay. Yes, that's good. This is good. Okay. All right. Thanks again to all the sponsors. Thank you to DevTO. Thanks to TWG for hosting. Right, and thanks everyone for coming and letting me talk about something that I think is interesting and important. So I gave a talk kind of like this a while ago here. It was just in the boardroom to TWGers. It was called Functional Programming with Elm. That was an hour-long talk. It's online. This is going to be 15 minutes, so I really had to pare it down and get to the point. And the point is, I think you should be functionally programming with Elm. That's kind of what I'm getting at here. Okay. My name is Mark Blusmiak. If you remember my last name, you can email me at blusmiak@gmail.com. On Twitter and GitHub, I'm Set5H. Okay, we're going to start with a little story game. I tell you a story about my experiences writing software. If you think that story is true and accurate, you give me a thumbs up. If you think maybe I'm lying a little bit, you give me a thumbs down. Okay? I once, in my whole life, accidentally tried invoking a method on a null object. And then I learned my lesson, and I never did it again. Who thinks that's right? I never did it again. Who thinks maybe it happens? Right. Okay. Okay. You guys are on to me already. Okay, here's another one. I once accidentally tried treating a value like it was a different type of value. I tried making a dog meow. But then I learned my lesson, and I never made that kind of mistake again. Who thinks I never made that kind of mistake again? Okay, maybe. Okay. Smart punch. Okay, I once, again, only once, didn't catch a specific type of exception I should have caught. And then I learned my lesson. I never did it again. Yes, thumbs up, thumbs down. Right, okay. Maybe you see a pattern here. I once accidentally used the wrong type of a quality check. And then, of course, I learned my lesson, and I never made that mistake again, right? No, I don't see a lot of thumbs up. Okay, so you guys figured me out. I keep making these same mistakes. I've been in the game for 15 years. I keep making the same mistakes. I think maybe others do too, right? The other truth is that languages exist where these types of errors cannot occur. And that's because types are enforced. Variables cannot change their type. Objects are immutable. They're always in a valid state. Objects containing the same values are equal, period. There are no nulls. Missing data and errors are made explicit in function signatures.
Erlang.
I don't know about Erlang. In any case, Elm is definitely one of those languages. And more specifically, Elm is a type-inferred functional reactive language. It compiles to HTML, CSS, and JavaScript. So it's for building front-end applications. It's for building the web front-end of your application. So the question is, why aren't we using these languages? If they're so great, why aren't we using them? We maybe think it's okay to repeat the same mistakes. I mean, we're shipping code, it's all good. We're getting paid, that's fine. Maybe we're not aware of the alternatives. For me, the big two were the alternatives have a steep learning curve, and I'm talking about Haskell, which was not acceptable. And this, talking to people who actually work in Haskell, it seems like it's taken them a long time to figure it out as well. I was at LambdaConf. I talked to a guy writing a book about Haskell. He gave a talk called How to Learn Haskell in Under 5 Years. Because it took him 5 years. So I mean, this is the sort of sentiment out there. In any case, some of the reasons we might not be using these languages is because they're impractical. There might be some weird esoteric sort of academic languages that are just, I mean, they don't have any useful libraries or whatever, so we're not using them. But Elm has a deliberately easy learning curve. I kid you not. It intentionally omits vocabulary and features that are hard to learn. So it looks at the developer, is aware of Haskell and all these cool features and stuff. And basically, they drew the line saying, this is what's important. This stuff is a little too complex, and we can do without it. So let's just make a language where people can use a pure functional language and get stuff done and get rid of the funny business. And that was on purpose. So me personally, I'm tired of repeating the same mistakes, and Elm is an alternative that is practical now. And so I think now is a good time to go learn some Elm. I don't mean like right now walk out of the door and get to it. I mean now in the history of programming, we have a pure functional language that is easy to learn. You can get stuff done. I think it's pretty exciting. Once you learn it, you could go write an Elm app, or you could learn that as a stepping stone to learn Haskell or PureScript. At the very least, you'll kind of know what the whole functional programming fuss is about, and you can spot functional programming techniques in other technology like React, Flux, Immutable, other things that are pulling ideas from the functional programming world. So it makes sense to do a quick tour of Elm. I hadn't been timing myself, so anyway. Here are a few sample expressions in Elm, just to show that there's nothing terrifying here. It's pretty straightforward stuff. And I'm going to run a few of these in the REPL just to see what happens. So if I say Elm is friendly, Elm says yes, Elm is friendly, and it tells me that that is a string. That's handy stuff. If I define a function, say hi takes the string hi and it appends x to it. If I define that here, it says, yes, what you have is a function, and the type of the function is something that maps a string to a string. So it actually looked at the code and inferred the type from it. I didn't have to specifically say, I'm going to declare a function that maps a string to a string. Elm just looked at it and said, hey, I know what this does. It maps a string to a string. So very cool type inference. Of course, once I define a function, I can use it. It's probably not surprising. And so on and so forth. So although Elm has very powerful type inference, we can use type annotations to make a contract between ourselves and the compiler, just as an extra sanity check. So I can say, look, I'm going to declare name, and it's going to be a string. And here, I say name is equal to this. And if for some reason I screw up and it's not a string, the compiler will call me on it and help me out. Again, we saw functions use the arrow to indicate mapping. So increment takes an integer and it gives another integer. Of course, we implement it by adding 1 to the value. In a type annotation, a type can be a variable. We know it's a variable because it's lowercase. And so singleton list takes a value of any type, and it gives us a list of that type. Okay, I hope that all makes sense. And again, I don't have to declare this stuff. If I just define that, Elm tells me, hey, I know what that is. That's a thing that takes an A to a list of A's. All Elm functions are curried. So what that means, and I'm going to show an example of this, all Elm functions are single parameter always. Even if you define them to take several parameters, under the hood, they're always a single parameter function. How this works is, currying takes a function of n parameters, and it turns that into n functions of one parameter, and it evaluates them sequentially. Okay? That means if I define a function add that takes a number and gives me a number, what that really is a function that takes a number, just one number, and it returns another function. That function takes a number and returns the result. I'm going to just show you that so you trust me here. So if I say add A and B, Elm tells me that takes a number and gives you a number. And if I say add 10 and 11, sure enough, it tells me that's 21. My claim was I could give that a single input and get another function out. I can use that function and give it another parameter. I could say, I can use that to define a new function. Add 10 equals add 10. And then I can say add 10 to 11. So that's what currying is all about. Currying takes a function of n parameters and turns it into n functions of one parameter that are evaluated sequentially. Why is this important? It's important because currying helps us easily build new functions. So string.contains of course, string.contains mark. Mark is coding is true. So it takes two parameters. It takes a string to look for and a string to look in. But just as easily, I can make a new function that checks to see if a string contains mark. That's like the easiest way to define a new function. It's just don't give all the parameters to another function. Boom, you've got a new function. It's amazing. Here's other ways that we can easily build functions in Elm. Let's say I have a negate function and I have an increment function, and I want to make a function that negates and then increments. So this what I've highlighted here is pretty standard. You'd probably see this in a lot of other languages, something like this. If you're used to using a Unix shell and piping values between commands, this will make sense. You can take x, you can pipe it to negate, and you can take the value and pipe it to increment. Yet another way of building functions is composition, which just glues basically two functions together and makes a new function. So I can say if I had a negate function and an increment function, and if I just fused those together in that order, then I would have a negate and increment function. So we have really expressive ways to put functions together and to partially evaluate functions, and it gives us a really expressive language. We've seen types thrown around, types that already existed. Types define the legal ways to put data together. If you want to make your own type, all you need to do is pick a name for the type and then declare some constructors for values of that type. So let's say I wanted to have a type called suits that could be diamonds, spades, clubs, or hearts. I just say that. And then if I type, if I say diamonds, then I get a value of diamonds, and its type is a suit. That's all there is to it. Very lightweight syntax for declaring what sort of data structures we can have. If I say a card is a suit and an int, then I can say card, diamonds, the 5 of diamonds, and the value of that is card diamonds 5, and it's a card. Its type is a card. I'm going to just gloss over this, but there's a syntax for creating records that looks like, if you're familiar with JavaScript or JSON, there's a syntax for that, for building nested data structures. Just know that it's there, and it's fairly straightforward. Types are very powerful. I can easily create a recursive type in one line, say for a list. I can say a list of A's is either empty or it's a node of A with another list of A's. And boom, I've declared a way of building lists. Once I've declared some types, how do I go about using them? Is everything kind of making sense so far? I mean, I don't want you to like walk away and you're like, I can make an Elm application. I just want to give you a sense of like, this is pretty easy stuff, it's pretty cool stuff, and that's kind of it. Anyway, once I have some types, I can say, okay, a flavor is either chocolate, vanilla, or strawberry. Size is either small or large. And to make an ice cream, I just say ice cream, I give it a size, and I give it a flavor. So once I've created these types, how do I use them? It's easy. I can say likes flavor takes a flavor to a Boolean, and likes flavor is true if f is chocolate. Pretty straightforward. Likes ice cream, I can match on the ice cream parameter and say, if that looks like an ice cream large, then let's look at the flavor and run likes flavor on it. Otherwise, false. So first of all, it's got to be large, and I have to like the flavor. Otherwise, I'm not interested in that ice cream. So it's very easy to use this stuff. How do we get away from using nulls? I said there was no nulls in these languages. We get away from using nulls by using a maybe. So like, just the same way, if I go up to you and I say, maybe I'm holding a sandwich, that means I'm either holding nothing or I'm just holding a sandwich. And that's what the maybe type is all about. And so when I run an operation that returns a maybe, then I match on what I get back. List.head, of course, if you give me a list that's empty, list.head of user list might be nothing. And in that case, I match on nothing and I say, okay, there's no users. Otherwise, maybe I'll get just a user, and I can do something with that. So boom, there's no more nulls. Similarly, there's no exceptions. There's a result type, which is either OK of a value or error with some sort of error detail. And I don't even have to look at what I got back because there are built-in functions that just operate on this stuff without me having to care about it. So I can map increment over a result. If the result is OK, then it gets incremented. If the result is an error, then I just get the error out. And what that means is I can chain together, I can use my composition to build these long chains of computation. And if an error happens at some point, there's no problem. The error is just going to get pumped out to the end. I don't have to worry about catching exceptions and like dealing with nulls and all this other funny stuff. I just throw things together. It's really beautiful and simple. I have to talk about purity. This is something that you might have heard of, this idea of functional purity. And very specifically, a function is pure if running it has no side effects and if the following always holds. Let's say I run this function with some input x. I have my function x, I have something x, and I call f of x, and I get a value back. Now, at any time in the future, if I run f at x again, I'm guaranteed to get the exact same result back. If I can make that guarantee all the time in my language, then I have a functionally pure language. Reasons why that might not happen is if f could mutate x, then that might cause problems. If f looks to some sort of global state, that could cause problems. That running the function might give me a different result. If f reads from a socket or a file, or even looks at the system time or something like that, then certainly f might give me a different number back. Or if something else affects f or x between calls, I could have the same problem, or running it again gives me a different value. If none of those things ever happen, then I can reason very easily about my programming language, because I just look at my function and I know it's just a function of whatever went into it. If I give it the same parameters, I'm going to get the same result. That's all a function is it's an operation on the inputs. Elm is a pure language. You cannot do impure things in Elm, right? Okay, so if I can't do input and output and change things and whatever, how the hell do you write an application, right? I mean, how do you do anything useful? The answer is that you write a few pure functions, and then you let Elm do the dirty work for you. So if you want to write an Elm application, and we're going to look at a very simple one, you basically need to declare two types and two functions. You need to say what your model is. Just declare some type for your model. Is it a list of stuff? Is it one of those sort of like more complex objects? Is it just a number? What is your model? You need to declare an action type, some actions that are legal to apply to the model. And then here's the interesting stuff. You need to write an update function, which says, if you give me an action and a model, I'll tell you what the new model looks like. Okay? You need to also say, write a view function that says, if you give me a model, I'll give you the HTML for that. There's this other little provision here for saying, here's a place to send action events when they occur. But really, this is the important part. If you give me a model, I can give you the HTML. These are pure things. Give me an action, a model, I'll give you a new model. Give me a model, and I'll give you HTML. These are pure things. They can't affect anything else. It's very simple and clean. Once you have those things, you plug them into your application, and you're done. You can't get into trouble. Your view code can't change your data. Your update function can't change your view. You're not going to break anything. It's very clean. It's very separate. Everything is a pure function. You just give it, it's very easy to test. You give it a value. You get a value out. And that's it. Very simple, very beautiful stuff. So again, to wrap up what we looked at, types enforce how data is organized. I think they're more expressive than classes. They're super lightweight. You can do recursive things. You can do all sorts of neat stuff. All values have a type. Functions map values to other values. And to build an app, you need functions with certain signatures. So if you kind of get that, then you can write an Elm application. Or you can certainly dig through the documentation and figure it out. So I'm going to show you a really simple example. It's taken from one of the official Elm examples. It's just a counter. I'm going to just increment a number or decrease a number, and that's it. the code is super straightforward. Like I said, we need to declare what our model looks like. And our model in this case is just an int. That's it. A valid model is an integer. Our view takes that model and it generates HTML from it. And it uses this very sort of clean syntax to do it. I'm going to create, if you know HTML, then this should look familiar. I'm going to create a div. There's going to be a button. Its style is going to be big. On click, I'm going to send to the signal address. I'm going to send it the decrement operation, and the text of the button is going to be a minus. Then I'm going to have another div where I toString my model. That's my output. That's where I see the number, and then I can increment the thing as well. So there's my view. Pretty straightforward stuff. You could probably read this and kind of understand it and make some changes already. The types of legal actions are either increment or decrement. And here's my update action. If you give me an action in a model, in the case that increment was the action, then I give you model +1. And in the other case, I give you model -1. And that's it. There's my application. I hope, does that kind of make sense to people? You look at that and you're like, that, I can read that. That makes sense. We could even say, whoops. Do I have a few more minutes? Yeah, okay. So really quickly, I'll just say, okay, so let's say reset, and we'll say reset, and maybe I have a reset action as well. So this would be reset, and in that case, I can just return 0. And if I reload this, whoops, reset. Let's see if it's, oh, you know what I did? It's saying, cannot find variable reset. So the reason is that I didn't say that it's a valid type of action. Okay, so here. Reset is a valid type of action. There we go. So now I can do whatever. I can reset it, so on and so forth, and reset it. So there we go. That's the simple demonstration, and I hope that all made sense. And this is where we can ask some questions. Yes?
This is actually really cool. What about designers who don't know coding? I mean, it looks like you basically, all of your stuff is kind of hardware.
So I kind of don't fully believe in that designers can't learn a little bit of code and vice versa. And so I kind of don't believe that, and I almost never see it. Like, so far in my whole life, everybody that designs knows a bit of JavaScript and so on and so forth. The other thing is that I think this is fairly straightforward to adjust things a little bit. And finally, you can just pull in external CSS. So I could just wire up some divs, and then a designer could mess with the CSS to work everything out. And I can just attach classes to things. So I think that's how using one of those things, like learn a little bit of Elm, or we'll kind of work together, or I'll put it together, you just deal with the CSS. I think one of those combinations would kind of get things done. Yeah. Yes?
How do you do asynchronous functions like Ajax and so forth?
Right. So the way that works is, I wanted to avoid that, but basically, it's a really good question. Basically, what that looks like is any action update takes an action and a model and returns a model, and it's something like a maybe, I can't remember what it's called. It's called like maybe effect or something like that. And if you return one of these, then an effect runs asynchronously and triggers an action back into this code. So a reset, so any of these would return the model, and they would either return nothing if there was nothing that I wanted to do, or maybe when I reset it, I want to tell someone about it, so I like fire off some effect. And so it's a very simple kind of like tweak from this. But the model is very, very similar. And so, yeah, that's it. So I can fire off a side effect. It gets processed asynchronously and comes back and updates things. And there's plenty of examples. And the community is really friendly, and the community believes that you know, they really want to make Elm a language that anybody can start with. Like, really, they believe everyone should be doing functional programming. It's the way to go. And let's do whatever we have to do so that this can be the first programming language of anyone, or so that anyone that has done any sort of programming can just jump in here and start being productive. So that's kind of what it's all about.
Thank you, Mark.
Okay, thank you so much.